Okay, let's get started, please. So, in some sense, this course is redoing stuff that you've seen in calculus, and just from a mathematically rigorous point of view. And that is basically what we're going to. That's basically the first result we're going to be talking about. Falls into that category. So, continuity and connectedness. So this is basically leading up to the intermediate value theorem, right? Do you guys remember? Does anybody remember the intermediate value theorem? Somebody tell me what the intermediate value theorem tells you. Yeah, read.
If you on an open interval A and B, for every f minus f of b, every value between those two will be obtained on the interval.
Okay, yeah, so you have basically, you have a function, it's continuous, so f a continuous function, right? F is continuous, and you have two points, a and b. Let's say that f of a is smaller than f of b. Then for every value gamma between f of a and f of b, f will attain that gamma somewhere, right? So given any gamma, in this interval, f of a, f of b, right, there exists a point c between a and b where f of c actually attains that value, right? And this doesn't. This actually has to do with properties of the real numbers. Okay. Okay. And so So this is what we're going to get to in a second. What we need to get this theorem is to see how continuous functions interact with connected sets. Okay. So recall, right? A set E is connected if it cannot be expressed. If it cannot be expressed as some union A union B, where the intersection of the closure of A with B is empty, and the intersection of the closure of A with B is empty, and the intersection of A with the closure of B is empty. I didn't say the same thing twice, but anyways. And right, so if it cannot be expressed as a union of separated sets, then we say that it's connected. Okay. And so we have this theorem that says that if you have, again, as usual, you have some metric spaces, and you have some function going from one metric space to another, and you have a continuous function and a connected set, then the image of that is still going to be connected. Okay. So the continuous image of a connected set is still a connected set. Okay. Right, and so we'll prove this by contraposition. We'll suppose that the image is disconnected, right? Suppose that the image can be expressed as a union of separated sets, and then we'll see that that E would have to be separated also. Okay. So suppose that f of E can be expressed as let's see what I use this notation, A union B, right? A union B, where, as usual, as above, the closure of A intersect B is empty, and A intersect the closure of B is empty. Okay. Then we're going to consider the set G, which is the inverse image of A intersect E, and the inverse image of B intersect E. Okay. Then E is going to be the union of G and H. Right? And we're gonna claim that these guys are that these show that. So we claim that that this will show E is disconnected. Right? It's not connected. It's not connected. And so the point is that if you look at G, well, G is F inverse A intersect E, right? Which is, of course, contained in F inverse A. Right? Which is contained in F inverse of A bar. Right? And H is contained in F inverse of B, right? Because it's, yeah, H is contained in H in F inverse of B. So then, right, so what's the point? If you look at the closure of G, so let me make the point before I go on here. Some good writing. G bar, since F inverse a closure is closed, G bar is contained, the closure of G is contained in F inverse A bar. Right. Right. Why is F inverse of A closure closed? Because what? Nope. Why is this closed? Well, because F is continuous and A closure is closed, right? And you know that if you have a continuous function, it pulls back open sets to open sets, and the inverse image of a closed set is a closed set, right? Okay. So by continuity, this guy is closed. Okay. So this is contained in there, and then now H is contained in F inverse B. So if we look at the intersection, G intersect H, well, that's contained in F inverse A bar intersect F inverse B. Right? But that's the same thing as F inverse of A bar intersect B. Right? But F A bar intersect B is empty. Right? Because these guys were a separation of F of E. So this is empty. Right? And so we see that G bar intersect H is empty, and similarly G intersect H bar is empty. So E is not connected.
How do we know that we can just that like the inverse function can just be like pulled out, and then A bar intersect B is like that second line is the same as the top one?
Oh, from here to here?
Mm-hmm.
Yeah, just think about it, right? What does it mean to be in the intersection of F inverse A and F inverse B? F inverse A had an F A bar and F inverse B. Well, it means that you are a point that gets mapped into A bar, right? And you are also a point that gets mapped into B, right? In other words, you are a point that gets mapped into A bar and also a point that gets mapped into B, right? So it's almost a tautology. Okay. Right. Yeah. Yeah. If you want, you can write it out. Yeah, more. Yes.
Why in the closure of G is the inverse of the A closure?
Right. So G is contained inside of this closed set, right? So G is contained inside of F inverse A bar, right? But F inverse A bar is closed, right? So if I go like this, right? This, if you have two sets, right? E contained in F, then E bar is contained in F bar, right? That's something that we used earlier, right? So now I'm gonna use that fact. I close both sides, but this thing on the right side, being closed already, doesn't change. It's easy. Don't, if it's not obvious, just go.
It is. I just didn't know that you're like allowed to just like make it like linear almost, where you just take it out.
Right. Yeah. So it's not true of all functions or something like that. But if you're looking at the inverse image, then this is true. Yeah. And in particular, you don't want to think of this. This is not really a function. So. Okay. So what we see is that if the image is disconnected, right, then if f of e is disconnected, then e must be disconnected also. So, e being connected means that f of e must be connected. Okay. Any questions? Any questions? Yes, Fernando.
I'm not very sure why E is the unit G and H. Can you
Yeah. Well, look, the image of E is A union B, right? So f of E, if we look at the inverse image of let's see, right? So E has to lie in F inverse of A union B, right? The image of E gets mapped into A union B, right? Right. E gets mapped into A union B, right? So E lies in F inverse of A union B.
Is it an equal sign or E is a subset? Since we define F of E to be A union B.
That's true, but F could have, F is actually a function on X.
Oh, okay.
Right? So there may be some guys outside of E that get mapped into A union B. Okay. And so maybe that's what you're worrying about here. That why did we have to intersect back with E? It's for that reason. Right. Okay. So, right, so E is contained in F inverse A, union F inverse B, right? In other words, E is going to be F inverse A intersect E, union F inverse B intersect E. Okay. Ariana, do you have a question?
No.
Okay. Are you all right? Somehow I feel like you're dispirited today. No? Yes, Andrew.
So just on the recall that
Yes.
portion.
Yes.
Why do you have? It's just the conditions. Maybe would it be too strong to say instead of those two conditions where they're both the intersections are equal to the empty set, to say where the closure of A intersect closure of B is equal to the empty set?
No, that's actually not the condition. Yeah.
Because it feels like from those two. It's
No,
like
it's not
almost-
true. It's not true. So, for example, right. Right. So. this is a disconnected set, right?
Yeah.
This is a disconnected set, right? But the
Oh, I see.
but the intersection of the closures is not empty.
Yeah. Got it.
Okay. Okay. So okay. So the continuous image of a connected set is connected, and that gives us immediately the intermediate value theorem in Corollary. Right. So right. So say f of a is less than f of b. So you have some function on an interval ab that is continuous, and if f of a is less than f of b, then for any c between f of a and f of b, there exists a point x in AB where f of x equals c. Okay. So that just follows immediately, right? Because of what? AB is connected, right? AB is connected. Implies that f of AB is a connected set. Right? But earlier we had that theorem that said in R1, what does it mean to be connected? It means that whenever you have 2 points, you have everything that lies between those 2 points, right? So that's the end, right? So just refer back to the previous theorem. My previous theorem, we're done, right? There's an earlier theorem that says, whenever you have 2 points in a connected set in R1, then you have every value between. Adam.
So why is this a closed interval? Does it need to be a closed interval? Because it doesn't seem to me that's necessary.
Just to have a value for f of a and a value for f of b. That's the only reason.
Sure, okay.
Yeah. Okay. Okay. Is everybody all right? You all seem you're really down or something. Did you all run out of energy over the weekend? Did you not sleep or something? Okay. Cheer up. Okay. Okay. Yeah. So let's go on. The next section, I have to say, I'm not really too enamored of. It's about monotonic functions and discontinuities and stuff. It's not all that important. But let's. I mean, it has some ideas that will, sort of basic ideas. So let's talk about them. But okay. So discontinuities. Discontinuities. Functions on R1. Okay. So just some introductory notions that you've probably seen before. So you have a function on some interval. Sorry. You have a function on some interval, goes in R1. You have a point in AB. Okay, and talk about what's called a right-handed limit. So right-handed limit, right? Which you've seen before, right? So it's a function. You have some interval a/b. You have some point x, right? And we want to talk about the limit from the right-hand side, right? Okay. So you can probably guess how we're going to define it, right? So if there exists a Q in R such that, given every epsilon, given any epsilon greater than 0, there exists a delta such that what happens? Then we say that the limit of f of x as x approaches, this is bad notation, let me call this point C, sorry. Now, I'm just going to keep it as x to be in tune with Rudin's notation. The limit of f of t as t approaches x from the right-hand side is q. So what should be the condition to call that a right-handed limit? Given any epsilon, what happens? Something from the right-hand side, right? Andrew?
So x plus any epsilon greater than 0.
Here's the epsilon,
maps
yeah.
to what?
Here's the epsilon.
Oh, sorry. X plus any delta greater than 0
Okay.
maps into that
Okay,
boundary.
yeah, so that everybody in a right-handed neighborhood, basically.
Right.
Right, so there's this delta such that if t lies in x plus delta, then f of t lies in the neighborhood, the epsilon neighborhood of Q. Right, so for the normal limit, we talk about, we say that there's a punctured neighborhood centered at x. For this one, we just want a sort of right-hand half of that punctured neighborhood, the right half of that punctured neighborhood. Yes?
Isn't it inclusive of x?
No, because we just want the limit to be q. We're not talking about the value at x itself. Okay. And Rudin's notation for this is f of x plus equals q. Okay. And similarly, we define f of x minus, right, the left-handed limit. And it should be pretty clear that if the left-handed limit and the right-handed limit are equal, then the limit of f of x, I'm sorry, the limit of f of t as t approaches x exists. That's equivalent to those both things existing. Okay. We can also talk about being right continuous at a point. Being right continuous at a point means that your right-handed limit equals your value there. Right? Your value at that point equals your limit as you approach from the right-hand side, right? And similarly for left. Being left continuous. And of course, being right and left continuous at a point means that you're continuous. Okay. Yes, Mona?
So instead of saying limit of ft exists, can we say the function is continuous at t?
No, because we don't know if the function has the value at x, right? right? So you could have the right-hand limit and the left-hand limit agreeing, but so the limit exists, but the function's not continuous there. Okay. Another term that Rudin uses, if f is discontinuous at x, but the left and right hand limits exist, then we call this a simple discontinuity. Or he calls it also discontinuity of the first kind. A discontinuity of the first kind. So, right, so the picture is, right, you're discontinuous at a point, but the left-hand limit and the right-hand limits exist there. So maybe something like this. Yes, Sam?
Do the right-hand limits and left-hand limits have to be equal, or do they just have to exist?
If they were equal, so they could be equal, right? They could be equal. Yeah. So this would also be a simple discontinuity. And then anything else is called a discontinuity of the second kind. Okay, so we're going to talk about monotonic functions and monotonic functions and discontinuities. Which is, all of you are yawning, and this, I'm afraid, is just going to make you yawn even more. Don't yawn too much, because it'll make me feel like I should just skip the section and let you read it by yourselves. Should we do that? No? Okay. That's actually what I would like to do, but yeah. Okay. Okay, here we go. Let's do it. Yeah, so hopefully we'll get to something that is at least exciting to me in a few minutes. Okay, so you have some function. First, what do we mean by monotonic? If x being less than y forces f of x to be less than or equal to f of y. So for x and y in AB, then we call f monotonically increasing. Right? And you can figure out what monotonically decreasing. So similarly for decreasing. Right. This is saying, of course, that whenever you have 2 points, right? If you know that whenever you have 2 points, the one on the left has a value that's less than or equal to the value on the right, then you know that you call this function monotonically increasing. Okay, it could be a flat function, right? That's still considered to be monotonically increasing. It could be something like what is so-called step function, monotonically increasing. Okay. So the result that we're aiming for is to show that the points of discontinuity of monotonic functions is countable. Okay, is a countable set. Right. So you have monotonic function. You have a monotonic function. It has some discontinuities. Right. Those points can only be, at most, they are countable. Okay. That's kind of interesting. So here's the theorem that will get us there. Say f is monotonically increasing on AB. Then for all x in AB, the right-hand limit and left-hand limits exist. Okay. So monotonic functions only have simple discontinuities. And in fact, the left-handed limit equals the supremum of f of t for t smaller than x. And that's less than or equal to f of x, which is less than or equal to the right-handed limit, which equals the infimum of f of t, where t lies between x and b. This sort of says what you would expect, right? You have some, what you think about a monotonic function, right? You have some discontinuity, right? You have some discontinuity here. The limit from the left-hand side is going to be the supremum of all the values, all the values over here, right? The limit from the right-hand side is going to be the infimum of all the values for points beyond x, right? And f of x has to lies between the left-hand limit and the right-hand limit. So it's sort of what you would expect, but let's prove it. So first off, let's start off with the claim that the supremum of f of t as t goes between a and x is the limit from the left-hand side. Okay. Actually, I'll let you do it. Take 1 minute and then give me a proof of that. Okay, first, you have to convince me that a supremum actually exists. Okay, talk to somebody nearby. Talk to somebody next to you. Say, I am so sleepy. It is not a thought in my mind.
That's the left hand. That's maybe
So what? So I guess
Okay. So first, somebody convinced me that the supremum actually exists as some finite number. Why? If we look at the values that.
I'm not sure what you said.
perfect timing.
Okay, so somebody, yes. So you've got all these values between. You've got f of t for t between a and x, right? Y, of course. So does that have an upper bound? Somebody tell me an upper bound. It will have a least upper bound if it has an upper bound by a least upper bound axiom, right? So what's an upper bound for it?
X.
Not x, but for these values, f of x, right? So certainly, right, f of x is bigger than f of x is an upper bound for the set of values, right, t between a and x, right? Right. So let's call so supremum exists. Let's call it A, just to use Gruden's notation. Right, so there is an upper bound, right? And we're trying to show that this is actually the left-handed limit, right? So want to show that A is A equals the left-handed limit, right? But right. So given any epsilon, right? So here, our fake picture is A, right? Okay. So here is x, right? So given any epsilon, we want to find a delta so that the left-handed delta neighborhood lies between a minus e and a, right? So how do we find our delta? How do we find our delta? Well, right? Do you know any point? Did anyone get this far? Anyone have an idea? Right, so you know that there's got to be, there must be some point x, right? X naught, sorry, smaller than x, where f of x naught is smaller than, is greater than a minus epsilon. Right? Because if there weren't, what would happen? This would not be the supremum. Right? We've seen this sort of argument before. Right? If there's nobody in there, then that's not the supremum. Right? Then this a minus epsilon would have been an upper bound for the set of values. Right? Okay. So we know that there's some point x naught where we take a value that is higher than higher than a minus epsilon, right? But then all the values past that lie between a minus epsilon and a, right? So we can just use this distance as our delta. This distance here is the delta we're looking for, right? We're looking for a left-handed neighborhood where everybody lies between a minus epsilon and a. Well, just find a point where you take a value that's bigger than a minus epsilon. Then that point is the boundary of the interval that we're looking for. Is that clear? Jonah, you looked a little...
That's fine.
Yeah, okay. Right. We're trying to show that given any epsilon, there's a neighborhood that gets mapped between the epsilon bars, the plus epsilon and minus epsilon bars. Well, because this value a is the supremum, there must be some point here that's between a and a minus epsilon, right? Since it's a monotonically increasing function, we know that all the points after that lie above this value, right? And they're certainly smaller than a, right? So everybody from here to here actually does lie between the epsilon bars. Okay. So take delta to be x minus x naught, then if by monotonicity, any t in x minus delta x satisfies f of t lies between a minus epsilon and x plus epsilon. Okay, and so a is the left-handed limit. Oops. Yes, Fernando.
I'm still not convinced about the existence of the x naught. Well, are we assuming any we're not assuming that the function is continuous, right?
No, just monotonic.
Yeah.
Yeah.
Well, is it possible that f of x naught is less than a minus epsilon?
Well,
For
so
all
what
x naught.
so what you're saying is that suppose that there's an epsilon and there's no values to the left here that lie between a and a minus epsilon, right? But in that case, a is not the least upper bound, right? A is, remember what a is? A is the least upper bound of all values between f of t between a and x, right? Well, if there's nobody here, right, that means that a is not the least upper bound. A minus epsilon is an upper bound of these values, but then a was not the least upper bound. Okay. So right. So f of x was an upper bound. One, we saw that f of x is an upper bound for this, right? So what we have at this point is that the supremum is equal to the left limit, right? And we also know that that f of x is bigger than or equal to it because remember f of x was an upper bound, so it's certainly bigger than the least upper bound. Right? So we have this, and we have this. Okay. And then you can see that just do the same argument on the other side, and you get the other two immediately. Okay. So now for part 2. In fact, I didn't put up part 2. So this is the proof of the first part here. So let me call this part 1 of the theorem. Part 2. Part 2, for any x less than y that lie in the interval ab, we have f of x. The right-handed limit of x is smaller than or equal to the left-handed limit of y. So here's A, again, here's A and B. You have x and y that are, x is less than y, and what we're saying is that the right-handed limit at x, the right-handed limit at x is less than or equal to the left-handed limit at y, which again is something that seems pretty clear, but let's prove it properly. Right. So, basically the proof of this is take a look at. Let's just. I'm sorry. Let me just tell it to you. If you look at this thing here, f of x plus is the infimum of f of t, where t lies between a and b. Right. It's the greatest lower bound of these values. Right. But that is the same thing as the infimum of the values from a. Sorry, that should be an x. From x to y. Right? Because the values between y and b are just bigger values. Right? So I'm not going to change the lower bound by adding in some bigger values. Right? I can throw out the values between y and b, basically. But that is, of course, smaller than the supremum of the values between y and t. Right? And you can see what I'm going to do, right? That is equal to the supremum of the values between a and y, which is equal to the left limit of y. The point is basically that when we're talking about the right-hand limit at x or the left-hand limit at y, we don't really care about this stuff here, right? Between a and x and y and b, right? We don't care about that stuff, and so you can basically just use part one, between x and y. Right, and then between x and y, it's obvious that that the infimum is less than the supremum. Okay, so let's get to the punchline, because that's the vaguely interesting part about this, that if you have a monotonic function, f monotonic on AB, then the set of discontinuities is at most countable. The set of discontinuities is at most countable. Okay, so it's either finite or it's countable. Okay, so the idea of this is pretty simple. What you say is that, well, look, consider, say that f is discontinuous at some point, some x. Okay. Right. So there's some point x, and you know there's a discontinuity there. Okay, so you've got a monotonic function right? It's defined. It's defined at every point, so it's not. There's no discontinuities due to a lack of definition. Okay, it's defined at every point. If it's discontinuous there, the discontinuity is simple. Right? The discontinuity is simple. So that must mean that the left-hand side, the left-hand limit, is strictly less than the right-hand limit. Right? You don't have to worry about it being less than or equal to, because if that were true, it would be continuous there. Right? Because it's defined there, the values would be equal, right? And then it would be continuous. Okay. So any monotonic function is going to have this sort of gap here. And so we just want a way of counting the gaps. And what we do is we say, well, look, by the Archimedean principle, or no, by density, excuse me, which follows from the Archimedean principle, we know that we can always pick a rational number between any two real numbers. Okay, so for every one of these guys, we associate a rational number. Okay, and then that shows that it's countable. Okay, so that's it. Do you want me to write it out? I can write it out. Right. By density, there exists a rational number such that R of x lies between f of x minus and f of x plus. Right. Further, we know that if x1 is less than x2, then f of x1 plus is less than or equal to f of x2 minus. So R of x1 is not equal to R of x2. This is just to ensure that we don't assign the same rational number to different discontinuities. It's impossible, right? It's not going to happen. So, so the number of discontinuities is less than, is less than the cardinality of Q, and so it's at most countable. The number of discontinuities can be placed in a one-to-one correspondence with some subset of Q, and thus is either finite or countable. Yes?
Can you explain why it's strictly f of x from the left or from the right is less than f of x from the
This
left?
one?
Strictly? Yeah.
Yeah. So you're worrying that you might have something like this, right? The limit from the left equals the limit from the right. But this function, remember, this function is defined at every point on AB. So what then is its value at x? Well, the value at x has to be that value. But if that happens, it's continuous there, right? And we're talking about a discontinuity.
Wait, how do you know it's defined at every point?
Just
That's
here
part
it
of
is,
the
right?
definition of
Yeah.
monotonic?
You have a monotonic. No, it's just you have a function on AB. Right, this is its domain, AB. Right, it's not. We're not saying f is defined in. We're not saying that f is defined on AB, excluding
Can't
some
you just
points.
have like the point be like about like higher or lower than?
No, you can't. Right, because if you had a point higher, that would make the right hand. It's a monotonic function,
Oh.
right? So you can't have that. That would make the.
It wouldn't be monotonic.
Yeah. Okay. Okay. Okay, so the last thing in this section is talking about limits and infinity. right? So basically, we want to talk about what do we mean when, what does the limit of f of x as x goes to infinity equals L mean? Okay, so just think about the normal finite definition, right? It means for the limit to be L means that, you know, as you approach some finite point C, so in the finite case, right, we mean that given any neighborhood around L, there's a neighborhood around C that gets mapped into there, right? Given any neighborhood around L, there's a punctured neighborhood around C, right? So given any neighborhood around L, there exists a punctured neighborhood around C, so that F maps that punctured neighborhood into the epsilon neighborhood of L. Okay. So if we're talking about x approaching an infinite point, the only thing we have to worry about is what do we mean by a neighborhood of infinity, right? What do we mean by a neighborhood of infinity? Well, all we mean is that, so here's the definition. For any C in R, any point C in R, we call the interval C, infinity a neighborhood of infinity. Okay, and then we just replace the neighborhood of C with the neighborhood of infinity here. Okay, so definition. If for all epsilon greater than 0, there exists a C such that f of the neighborhood of infinity is contained inside of the epsilon neighborhood of L, then we say that the limit of f of x as x approaches infinity is L. This is for a function going from R into some metric space. Right, and L is some point. Sorry, that should be here. Sorry. Right, and L is some point in the metric space. Right, L is some point in the metric space. Okay, so it's basically the same thing as before, right? Previously, here is L, and here was C, right? For the limit to be L meant given any neighborhood around here, there's a neighborhood around C that gets mapped inside, right? And now what we're saying is that given any neighborhood around here, there's a neighborhood of infinity, right? There's a neighborhood of infinity, so that everybody in here gets mapped inside, right? And that means that the limit as x tends towards infinity is L. It's not all that different a notion. And then the standard theorems still hold. Right. If you look at the limit of the sum of functions as t goes to infinity, well, that's just going to be the sum of the limits as t goes to infinity. So, just like the regular theorems still hold. The proofs are basically identical. Okay, let's go on. Now that we have limits, just sort of following the basic path of calculus. Now that we have limits, we'll talk about derivatives. So chapter 5, differentiation. But hopefully, we'll give you a better sense of what differentiation is. Now that you're grown up.
Question.
Yes?
Will we chapter 5 on the midterm?
Will chapter 5 be on the midterm? Let me think about that. Okay, let me think.
When is the midterm?
Next Monday. Yeah. So probably not. Right? Probably not. Okay. So differentiation. You all know what differentiation is, right? We're not doing this in any different setting, but hopefully we'll do it in a deeper way so you get a better understanding of what actually happened back in calculus. So say the function on some closed interval into R, if the limit, so let's say x is some point in the open set there. If the limit of f of t minus f of x over t minus x as t approaches x exists, then we call it f prime x and say that f is differentiable at x. Okay. So an old reassuring statement. Okay. Something that you've seen before, that if f is differentiable at x, then f is continuous at x. Okay. Does anyone know how to prove this? Anyone know a proof of this? How do you show that differentiability implies continuity? Andrew?
Because, I don't know if this shows it properly, but because the limit says as t approaches x, so that has to exist from all sides, the plus and positive and negative.
Sure.
And if those two are equal and they're both that, and that's the only way for that limit to exist, then it has to be continuous and stuff.
But why does that have to be continuous? So you have to think about what continuity means, right? Continuity means that the limit, right?
Well, the limit from the positive and negative both exist, and also it's continuous. Oh, yes.
Yeah,
Well-
certainly that this limit exists, right? But what limit do you need for continuity to exist, right? For continuity, to show continuity, you need to show that the limit of f of t as t approaches x equals f of x. Okay, right? So this is the limit that you want to show. This is the limit that you have,
Okay.
right? Okay, so certainly this limit exists from the left and right side, but you're not. We need to talk about this limit,
Right,
right?
that
Okay,
makes
so
sense.
yeah, does anyone remember this? Did anyone see this in their calculus class? You didn't. It's okay. Okay, so consider the limit of f of t minus f of x as t approaches x. Right. If we show that this is 0, then we're done, right? So I want to show it equals 0. Well, this thing here equals the limit of f of t minus f of x over t minus x times t minus x. Right? It's okay to multiply by 1. Okay, we've just multiplied the thing by a funny-looking 1. T minus x over t minus x. Right? And we're not doing anything illegal because t is never equal to x. Right? We don't care what happens when t equals x. Okay. Okay. So now you just use one of your basic limit theorems. The limit of a product of functions equals the product of the limit of functions, right? So one of the theorems in your book, we didn't mention it, but I hope you looked at it. The limit of the product of functions as x approaches c equals the product of the limits of the functions. Right? As long as these limits exist. Right? So as long as these limits exist independently, then the limit of the product equals the product of the limits. So something that I hope you read. Okay, so this is going to equal to the limit of t minus f of x over t minus x as t approaches x times the limit of t minus x as t approaches x. Right? And so I said, this splitting only works if these limits exist independently, but they do, right? This limit is 0, and this limit exists because we assume the function to be differentiable, right? So this limit exists because of our hypothesis, right? This limit exists because this limit exists, right? Okay, so we end up with f prime of x times 0, so that's 0. Yeah, so be a little bit cautious about playing this trick unless you know. You have to know that both of the limits exist. Yeah. Okay. So I think we'll stop there. Next time we'll do a bunch of properties of differentiation and get to the mean value theorem, which is pretty cool. So I hope that will be more eye-opening than this one.